One of the fundamental questions we ask ourselves when looking at the sky is, are there others out there like us? For the past several decades, scientists have been looking for the answer to this question. How do they do this? What qualities do they look for? When looking at exoplanets, that is, planets outside of our solar system, scientists first try to identify if that planet lies within that star's habitable zone. A habitable zone is the orbital zone around a star in which an exoplanet has the potential to host liquid water on its surface, which we believe is a precondition for life. Earth is in the Sun's habitable zone. If an exoplanet is too close to its star, the planet will be too hot and water will evaporate. Think of the hot world of Mercury, which lies very close to our Sun. If the exoplanet is too far away, the water will freeze. A star's mass, age, temperature, and luminosity, also known as brightness, influence where and how big a star's habitable zone is. Scientists look closest for exoplanets around low-mass main-sequence stars, which we can see along this line here. A star's habitable zone changes throughout the star's life. Habitable zones are usually not possible at the beginning of a star's life, and the habitable zone may move farther out when the star becomes hot later in its life cycle. Let's look at this simulation of the evolution of our Sun's habitable zone. Here we see our planet nestled comfortably within the habitable zone. If we decrease the Sun's mass to 30% its current mass, the habitable zone is much smaller and closer to the Sun. Note that the temperature of the Sun is only 3,580 degrees Kelvin. As we increase the Sun's mass and temperature, we observe the habitable zone expanding and moving farther away from the Sun. If the Sun's mass were 120% its current mass, its temperature would be 6,250 degrees Kelvin, and the habitable zone would be surrounding Mars, and water could no longer survive in a liquid state on Earth. The search for exoplanets is a relatively new field. The first exoplanet around a main sequence star wasn't discovered until 1995. Since then, efforts to find exoplanets have increased greatly. The Kepler telescope was launched in 2009 in order to find exoplanets. Since then, it has confirmed the existence of 961 planets and has observed over 2,000 planet candidates. Kepler finds exoplanets through a method called transit. There are other methods to detect exoplanets such as radial velocity, astrometry, and imaging. Transit has proved by far to be the most successful, so we will focus on that. Transit is when a planet passes in front of a star. When a planet passes in front of a star, there is a decrease in the amount of light that we can observe from that star. The closer an object is to the star, the easier it is to detect because it blocks more light. It is also easier to detect a large planet, which is why most of the first exoplanets we found were Jupiter-sized planets that orbited close to their star. We called these exoplanets hot Jupiters because they were similar in size to Jupiter, but they were much warmer. If comparable decreases in light caused by transit are observed multiple times, we can confirm the existence of an exoplanet around that star. Recently, scientists have been focusing on finding exoplanets around red dwarf stars, since they are among the most common stars in our galaxy. Astronomers estimate that red dwarfs make up to 75% of the stars in the Milky Way. Because of their relatively cool temperature, the habitable zones are close to the star, which makes exoplanets within that zone easier to detect. On March 25, 2014, scientists confirmed the existence of an Earth-sized rocky planet within the habitable zone of a red dwarf star. Recent estimates claim that there could be as many as 60 billion exoplanets orbiting red dwarf stars in the Milky Way, with the potential to sustain water and life. One thing to remember is that just because an exoplanet is within the habitable zone does not mean that planet could host life. There are other characteristics such as atmosphere and planet composition to consider. If the atmosphere of a planet is too dense, then the planet will be too hot. Venus is an example of this, since the high concentration of carbon in its atmosphere has led to a runaway greenhouse effect on the planet. We are more likely to find life on a rocky planet like Earth than on a gaseous one like Jupiter. However, we are coming ever closer to finding a planet which could host life, like or unlike life here on Earth.